What's up, everyone? This is LeetCode 46 Permutations. We've done this problem in Python. Now we're going to do it in C++. So this is very similar. It's not that similar to combination sum, but we just did combination summing on the Grind 75 list. Now we have to do permutations. So in this case, right, permutations, basically the order, you basically have to arrange all the elements of the array, right? So in combinations, for example, right, if you have something like 1, 3, 2, you can't include something like 1, 3, or 1, 2, 3, you can't include something like 1, 3, 2. But in permutations, you can, right? So I'm going to show you 3 solutions from least optimal to most. But the reason I show you 3, even the least optimal, is because it'll help you understand basically how you handle this problem. Because I think the goal of this problem is very simple, right? You're given an input array and you have to return the permutations. The goal is simple. The implementation is a little bit more difficult. So I want to show you the least optimal solution just so you kind of understand what we have to do, so that when I optimize it, you kind of don't get lost. Because I think if I show you the fastest, most optimal way first, I think it might be a little bit confusing. So I just want to go step by step. Okay. So we can think of this problem like a decision tree, obviously, right? To build out our permutations, right? So we have 3 elements. We can take either 1 or 2 or 3, right? If we take a 1, then we have to take a 2 or a 3 to build out our permutation. So if we take a 2, then we can get a 3. If we take a 3, then we can get a 2, right? Right. Likewise, if we take the 2 first, we can take a 1 or a 3, and then we either take a 3 or 1 depending on what we chose above, right? So the reason I draw this is because you either care about a number or you don't, right? And so it's important to know that that's an important factor for us, right? Like if we choose a 1, we don't want to choose a 1 again. If we choose a 2, we don't want to choose a 2 again, right? So it is an important criteria. And I'll briefly explain kind of how our algorithm is going to work. So we're basically going to do a recursive call within a for loop, right? And we're going to basically say, okay, wait, so we have a for loop with some inputs, right? Like 1, 2, 3. And what we're basically doing is we're basically iterating through this for loop, right? And if we have a number that we have not seen before, let's add it to our permutation array. So when we iterate through this, we have a 1. So let's add it to our permutation array, right? Now we do the for loop again, because again, this basically recursion is within a for loop. So okay, 1. Okay, this one's we already chosen our permutation array. What about this 2? 2 we don't have, so we can add the 2 to our permutation array, right? Then we do it again. Okay, 1 we already have, 2 we already have. Oh, we don't have 3. We can add 3. So our permutation array is like this. Okay, so now our permutation array is equal to the length of the input. So we know we can't add anything else. So let's add this and put it in the answer array. Because if you remember, the answer array is basically an array of arrays, right? So we need to add all these different permutations into the answer array. Okay, so we add this array to the output array. And now what we do basically to handle the other permutation is we're gonna pop this last element, right? Because we're done with this call stack. Okay. And we're gonna pop this because now we have 1 and 2, right? We're on the second call stack. Well, there's nothing. So we already had a 1. We already had a 2. We added a 3, but we already popped out of that. Well, there's nothing else to check, right? So when we go up the stack again, we pop the 2. Now when we pop the 2 though, we have to still handle the 3, right? So we in that for loop, in that call stack's for loop. So we go to the 3, we add that. Okay. And now we do again. Okay, is 1 in the permutation array? No. Yes, it is. Sorry. 2? No, 2 is not. So now we have 1, 3, 2 that we can add, right? So we added 1, 2, 3, and now we add 1, 1, 3, 2, right? And so then basically we backtrack all the way. So we added. So now we basically for the first for loop, now we move on to the 2. Boom, right? And so now we do the for loop again. Okay, 1 is not in there. 3 is, right? We pop out. We pop out. We're for the 1. We have to still check the 3. So we have 2, 3, 1 for the third one, right? Yeah. So that's basically how our permutations are, our permutation kind of logic is going to work. So I hope that makes sense. I don't think it's actually that difficult to understand this least optimal approach. But I will say this problem definitely took me a while to understand. So don't feel bad if that's the case for you. I think the biggest tip I can give is make sure you try not to memorize everything in your head in terms of the call stacks and how to visualize what is happening. Actually draw it out somewhere. It will help a ton. I promise you, it will help a ton. And the code will actually make sense, and you'll be able to actually understand how to approach this problem next time you see it around. Because, if this is the first time seeing this problem, you're going to forget it. It's just natural. Okay, so we're gonna have an answer array, right? This is what we need to return, right? So we're gonna say vector of a vector answer. We have to return this down here, right? And actually, let me switch over. I'm in Python still. Gonna have this. Oop. Okay, so we create our answer array, and we also have to create our permutation array. So we're gonna say our vector. Actually, it's not a vector of a vector. It's just one vector. The reason our answer has to be a vector of a vector is because we have to return an array of arrays, basically. So we do this. Okay. Now we have a backtracking function that we can create. I'm just gonna do it within this function, right? So we'll say function void. We're gonna call it BT for backtracking, right? So we're going to say, we're gonna say basically if the actually before we do that, we need to do something else first. So what we have to do is we have to return. So like if we have just this, right? There are no permutations except itself. So we just return this input as a. So this input's an array, and we have to return that within an array, right? Because we have to return an array of arrays. So be careful about that because you don't want to return this element because you don't want to return something like bracket one bracket. It has to be an array of arrays still, right? Even if there's only one element. So just be aware of that. So we're gonna say if nums dot size is equal to 1, gonna return nums, right? Okay, so I had to fix this. Make sure we keep our coding style proper, right? We're in C++, so we don't want to use an underscore here. Just for naming variables and our data structures and stuff. So first of all, we need to remember what our base case is on when we should break out of our function. And first of all, we have to create our function, right? So we're gonna say function, and our function is our recursive function, right? That's what I mean. We're gonna call it BT for backtrack. We're gonna say this, right? That. And we're gonna say basically if the length of the permutation array ever gets to a point where it's the same size as the input array, that's when we know we have to basically take our permutation array, put it in the answer array, and then return up the call stack, right? So we're gonna say if perm array dot size is equals to nums dot size, right? In that case, we want to take answer, push back onto it whatever's in the permutation array, right? Boom, and then we return. Boom. Okay, now here's basically where we do our recursive call stacks for our for loops. So we're going to say for it. I think I accidentally submitted earlier, by the way. This is why it's here. Don't worry about that. Because we're still writing our code, right? So here we're basically going to get a number and we're going to iterate through nums, right? Remember that's what we have to do every time in the call stack. And basically what we're going to do is we first need to check, okay, right? Is X in permutation array? If not, add it, right? That's simple, right? So we're going to say defined perm r dot in perm r dot end x equal perm dot, right? So we're going to say perm r dot pushback x, right? Then we're going to keep recursing. And after we exit this recursive call, we're going to do pop back because we need to pop it, right? And then down here is where we actually call this function, right? Okay, so this is kind of the least inefficient approach. So keep that in mind. Whoops, expected semicolon. Oh, right, because it's our function. Oh, down here, I was when I was messing with my switching it to Python and stuff. So we want to return our answer array, right? Okay, so this is our least inefficient approach. If you want to know what this code is doing, you can just scroll back to where I was doing the illustration. But we're basically just recursively going through this for loop and basically seeing if every number at a given call stack is that number in our permutation array, and that's how we build out our permutations. Okay, and obviously we make sure we pop so we can keep getting all different types of permutations. Okay, so this is the least efficient, and then we're going to go into the next one now. Okay, this second solution is basically the same as the first one, except you know how we're basically all right, this second solution is basically the same as the first one, except we're using stdfind to find whether x is in the for loop, right? Well, the issue with that is this is O of n, right? So the possible permutations is O of n factorial, right? So for length of nums, which let's call it n, there's n factorial permutations, right? So if we do it this way, our time complexity is going to be O of n times n factorial. We can reduce that down to O of n factorial, but we use a little bit more space by using a set, okay? And so we can make it slightly more optimal just by doing that, right? So we're going to keep this the same, right? This is our base case, right? When we have one element, and this here we can delete, right? We can use a set here. Obviously, our output answer has to stay there, right? Because we have to return that. So here we can just say unordered set int used, so we can keep track of the numbers we use. And again, all this is for faster lookup, right? So that we can cut our time complexity down, right? Because of how efficient lookups are for hash sets. Okay, so we're gonna keep this the same. We're gonna keep this the same, except we're going to pass it an input of permutation sets, or a permutation array, I should say. So actually, we will keep this, right? We will keep this. Right, we'll just create it right down here. Again, we use a little bit more space using a set. But kind of the point is that we're not going to we're going to cut down on some time complexity here with the lookup, right? That's kind of the point of that. So we're going to say permarray.size is equal to nums.size, right? This is the same to basically let us know when we have to break. Right? So we can say, and let me just comment this a little bit just to make it easier on you. So basically, if the current permutation array has the same size as nums, add it to the answer. Okay, now down here, again, this second solution I'm showing you now is functionally all the same. This is the only important part that's going to change, right? So we're going to say if used dot find x is equal to used dot end, right? If x not yet used, right? Then we can basically add this to our set, this x, right? Push it back, right? We're going to do bt perm r. We want to pop it back. And then at the end, when we pop a permutation array, right, we're backtracking up a level. So we actually want to remove the element we added. Okay. And I think that should be it. Line 32. Oh, sorry, this function up here. Want to make sure we have a void function, void vector int, and our input, right? And just like that. I'm not too used to inline functions, C++. I'm not the greatest C++ user, so apologize for that. But that's not the important part, right? That's just syntax stuff. The important part is that you get the logic which is happening here, right? So this is the second solution. We're using a hash set now. Did I say hash map earlier? If I said hash map at any point, I'm sorry. I meant a hash set, obviously. If we're using a hash set for faster lookup, for looking up if a number is in our if a number is in our hash set, then we know that we can skip it or take it depending on whether it is or not, right? And it's just for lookup, right? Just to cut down our time complexity a tiny bit, okay? So now I'm gonna show you the third solution, okay? All right, this is the third solution. So why did I show you those first two solutions? Well, because I just want you to be able to visualize and kind of understand somewhat what's happening. First, before we do this third solution, because this third solution can be a little bit hard to visualize, kind of the call stack in your mind. It's kind of conceptually the same as the first two, except we're not going to use any extra space. So the first solution that I showed you is O of n times n factorial, because our lookup was pretty bad, right? Now the second solution I showed you is O of n factorial, time complexity, but we use a little bit extra space. Now I'm going to show you O of n factorial time complexity, but the space is going to be less, right? So this is kind of the most optimal solution. Okay, so first of all, let's create our vector of vectors, right? This is important. This is our answer. And this is what we have to return, right? And again, we're going to create a function, right? A helper function for backtracking. So we're going to say function void int and et equals, and we're going to say int start index. Okay, we're going to pass it a start index, and it's going to basically be kind of like a pointer of where we're currently at. And I'll show you in an illustration how this works, right? I think I might want to write the code first, and then I'll show you. So we're going to have basically a starting index that's going to be at the 0th index first, right? And we're going to use that to basically traverse through our array. And basically, if the starting index ever gets to the end, so if start index equals num.size, that's basically our cue to push something to the stack, or not the stack, sorry, to push something to our answer vector. I call it an array, but you know, vector and array, I just use those interchangeably, so hopefully I'm not confusing you. So we do this, okay? Let me just write this here. So end of the helper function, okay? So this is kind of similar to our first solution, second solution, sorta, but it's going to differ a little bit in that what this solution is going to do is we're going to basically swap the elements and do a recursive call that way. And then when we're done with that, we're going to swap the elements back, okay? So what we're going to say is we're going to say for int I is equal to start index. So notice that the I is going to start at the starting index, and we're going to go forward from there. So we're going to say for int I is equal to start index. I is less than nums.size I plus plus, right? And we're basically going to do the swap. I think you can use swap if you want. Maybe I should do it like, I mean, I don't know. You can do it manually if you want. Because I was thinking like, do I use this built-in function or do it manually with like a temp variable? I mean, you can do it either way. Like it shouldn't. I don't think this is like a simple video where you need to. The whole point is to manually swap stuff, but make sure you swap it, right? So here we're basically swapping the elements at start index and I. Again, you can do this manually if you don't want to use a built-in function. I don't know. It depends. Some interviews might let you get away with it. Some not. I mean, it's not that hard to implement a swap function, or not even a function. Just do it in the for loop, right? We're just swapping elements. That's all we're doing. Okay, nothing complicated, right? And then we're gonna basically recursively call into BT, and then here is basically swap elements back to original place, right? And I believe that should run. So this code is actually pretty simple. Function. So we're gonna say function void int and BT and int start index. Oh, this should not be here. I'm sorry. That was my mistake. Again, I think I said this Oh, this is, yeah, this is a function. Like I said, I'm sorry, I don't use like inline functions, helper functions, C++. I usually like create like a separate function outside. So that's just my fault, just a little syntax stuff. But anyways, this code is pretty simple, but it may be a little bit hard to understand what the heck we're doing with the swapping. I'm going to show you an illustration, okay? So let's go down here, okay? So initially, what we're doing is we're starting at start index is initially 0, right? And we're using the for loop to iterate, okay? And again, the I is always going to start where start index is and work forward. So we're going to swap I and start index. So obviously they're the same thing. They're at the same place initially. So we're going to basically swap those, enter, and then enter the function again, and do start index 1. So we're going to go here. And again, these are going to swap with each other again. So technically nothing's going to change. Then we move forward. These are going to swap again. And then we move forward again. And we're out of bounds, right? Because start index is equal to nums.size, okay? So when we're here, we're going to push onto the answer, whatever nums is. So 1, 2, 3 gets pushed onto the answer, okay? And so the way we're going to do this is when we go back up the call stack, right? And we go back here. Well, there's nothing to keep iterating for the I, so we're going to go up the call stack again, right? And when we're here, right, when we were here, right, we keep going forward. So we're basically working our way back now. Now, when we're here, the I can move forward though, right? Because it's not done yet. The for loop is not done yet. So that technically this I moves forward now, but starting index is here, right? So now these two get swapped. So we go 1, 3, 2, right? And then we move forward again until s index is out of bounds. So now 1, 3, 2 is going to get added to the output, okay? And we're basically going to go back, right? Right? We're going to go back and we're going to swap them back again, okay? And now we're basically at the start, except now the I is going to move forward. So we're starting index is here and the I is here. And now we're going to swap these two, okay? And you can pause at any point if you want to read some of these things. And by the way, I'm not going to claim this diagram is completely perfect. I kind of drew it really fast, but it'll get the point across on kind of visually on what's happening. So the I is here, we swap these two, right? And so now the starting index is technically here. Well, no, it's here, but we do s index plus 1. So we move forward, right? And we do here. We move forward all the way again until we get to the end. And now we have 2, 1, 3, right? So 2, 1, 3. And again, on our way back, right? When we get here again, the I has to move forward. And so then we would get 2, 3, 1, right? So in short, what we're doing, right, is we're basically building up permutations where the first number is going to be some particular number like 1 or 2. And we go to the end. We go to the end of the array, right? And then on our way back, we make sure we get all the other permutations, right? So we do 1, 2, 3. But on our way back, we need to make sure we handle not just 2, 3, but 3, 2, right? That's kind of how our swap works. I honestly think this third solution is really optimal. It is optimal, but it's a little bit hard to understand visually what you're doing because like you gotta like think about, okay, what gets swapped where? How do we keep going forward with those swaps? Oh, then on our way out, then on our way back, we have to swap them back. Like where do things get swapped? Where do they get unswapped in the call stack? Like that type of stuff is actually a little bit hard to visualize. So that's why I drew this out. If you're still confused, I recommend doing it yourself, like drawing this out by yourself. But I think it gets the point across. So this is the optimal solution. Maybe there's a more optimal one out there, right? You can let me know, but this is O of n factorial time complexity, and we're not really using any space, right? I don't think you usually count the output array as extra space, but yeah, they should do it. So yeah. Very simple problem on the surface, but implementing is a little bit tricky, right? But I hope this helped, and I'll see you in the next one. Peace out.